Hey, what's up, guys? This is Chung here. This time let's talk about a graph problem here. So it's called it's number 332 Reconstruct Itinerary. So you're given an input for the itinerary with each element in the array gonna be the flight from airport and to airport. So this one from Munich, right? The MUC to LHR, I don't know where it is. And this one from JFK to MUC, San Francisco to SJC, yeah, so on and so forth. And you need to return a path, basically, right? Basically, a path starting from JFK. So basically, you have to start with JFK and starting from JFK, and you need to uh, use all the tickets once and only once, right? So what does this mean? So basically, you're giving like the tickets you can only use those tickets once, but you have to use all the tickets, right? So obviously, this is going to be a problem, right? Because with all the tickets here, with from and to, we'll be constructing a directed graph, right? And so the problem will be converted to traverse, right? To traverse each edge of this. So each edge will be from and to, right? So it's gonna be traverse each edge of the graph once and only once, right? And and one thing, yeah, so if there are multiple like ways of traversing this graph, and you need to return the smallest lexical order, yeah, right? For example, here, like there are two possible ways of traversing this graph, uh, uh, traversing each edge of this graph only once, right? One way is this, the other way is this one, but we're returning this one because the ALT is smaller than SFO in terms of the lexical order, right? So so when you see this like to traverse the edge once and only once, you know this is like a, if you know the term, it's called a Eulerius path. So for the Eulerius path, you basically you traverse this directed graph each edge once and only once, right? For example, this one here, and yeah, I'm gonna probably write a JFK here. I'm gonna use this one. I'm gonna use this one as an example here. So it's gonna be JFK, right? From JFK to what, to SFO, right? And JFK will also go to a ATL, and SFO will go to ATL, right here. And ATL, okay, will also go to JFK, and ATL will also go to, okay, SFO. All right, so that's the that's the graph, right? So how should we do it, right? So there are like several ways, but I think the most famous one is there was this Germany mathematicians, I think it's called Hierholzer, yeah, Ho Hierholzer, yeah, something like that. So he invented an algorithm in I think in 1873, yeah. So basically, what the algorithm does is from one node, from one node, you randomly pick any any direction, right? As long as there's a path, you just use that direction from you pick one and any direction, you just go along with that with that node. And while you're traversing it, so every time when you traverse, like follow this path here, let's say for example the JFK, right? Let's say we go with the SFO first. So once you traverse from this side, you just remove this edge from the graph, and then we just recursive calling the same issue, same like method. It will go to SFO, and from SFO it will also again randomly pick any edge from starting from this one, and it will go here until, right, until you reach a node that doesn't have any out any outgoing edges, right? Then we simply stop, because that node will be our last visit node, right? Because that's the we know we have to visit that node last, otherwise we cannot visit all the nodes once and only once, right? And we just keep doing it until we finish traversing uh, all the nodes here, right? Basically, every time, as long as that node has an outgoing edge, we just follow that edge, and we go to the next one. So basically, that's how the Hierholzer like algorithm to traverse this like Eulerian path. But remember here, so we are uh, for example here, for this path from JFK, right? We're starting from JFK. From JFK and SL, there are two ways, right? There are two outgoing edges, right? One is to SFO, the other one is for ATL. And if there are two options, so we it always wants us to follow the smallest, right? Smallest lexical order when read as a single string. So in this case, we'll always traverse uh, a smaller node first. So that will make sure our path will will have this one instead of that one, right? Because once we have all the nodes added to our result, we will just reverse the result array, because we're adding the last node, visited node first, and then we just keep adding it back. Okay, so I think yeah, that's pretty much about this problem. Let's try to code it, right? So one thing is that once we build, every time we will build the graph first. But remember, when we so usually when we build the graph, right? What do? We just create a graph, right? And then we just do like the dictionary, right? But in this case, since we want we want to choose this like the neighbors of this current node, like from smallest to biggest one. So we have to either we need to sort that list, right? Or we can use like a priority queue to sort the neighbors. So basically every time we can be sure we always get the smallest one, right? So let's use a priority queue here. So we're gonna we have to import that first from import queue from queue import uh, priority priority, right? Queue. And then we're building the graph first. So default dictionary, right? So for each of the graph, each of the element in the dictionary, we're gonna the value, the key will be the airport name, and the value will be the priority queue, right? And then we simply just construct this graph by looping all the tickets here, right? For ticket in ticket, right? Uh, origin, right? Origin and equals to destination, right? Destination basically equals to what? So basically the first one is the origin and the second one is the destination, right? And then we just build this like directed graph here. Graph uh, from origin dot, right? So since we're using a priority queue, we need to use a put, right? That's the method for priority queue, we put this destination to it. So that's how we maintain like a priority queue inside for this like for this our origin airport. Right. Then we're gonna have like an answer to store our results, and right, and now we need to create like a helper function, define like a DFS, right, helper functions. So here we're gonna have the node, right, and then so what do we do here, right? So with node, right, with node we get the next list, right? So that's the graph dot node. So this next list will be the all the all the nodes the neighbor nodes of the current node, right? So like what we said about this like algorithm while, right? We will basically will keep picking we'll we'll pick all basically we'll loop through all the edges starting from this node, right? Next, basically it's next destination, right? Will be the uh yeah. So this since the priority queue to check if it's empty or not, we can just check the queue size, right? The queue size is bigger than zero, right? So then we start. If it's zero, we know we have already consumed all the edges starting from this node. Next list dot get, right? So basically every time we get the first one, which will be the smallest. That's how we can be sure. We always select the smallest lexical mm, airport, right? Yeah, sorry, that's my Alexa. Yeah, and every time once we so every time when we finish traversing this node, this edge will be basically remove it from the priority queue. So the get will simply remove that's the first one. And then for each of the next, like I said, we just follow this path. We just keep calling, right? Keep calling this same thing over and over until, right? Until we have finished, until we finish all the traversing all the neighbors, all the edges starting for this node, right? Then we know we reach the last the last visit node, right? So we just do a answer, right? Dot append the current node, right? The current node, yeah, yeah. Actually, this is not a node. I would say like uh, it's a origin, right? So it's not a node. It's a string here. It's a value. So origin, and then yeah, and once when we finish traversing everything, so this answer will have all the answers starting from the last. So origin, yeah, yeah, and then we simply return the ANS, right? A reverse that, reverse that result. Yeah, here gonna be JFK, right? So it's a fixed starting point basically. And let's see, append. All right, cool. Let's see. Cool. Yeah, it's passed. All right. So I so why this algorithm works, right? Let's say we have this like JFK uh, uh, JFK, let's see, uh, LAX, right? And then MUC, right? Let's see, we have this graph, right? It's pretty easy, right? Okay, let's see how this thing will give us the final result, right? So we're starting from JFK, right? So from JFK we have assuming yeah, let's assuming we don't use a priority queue, we just use a random regular list. So from JFK, and we have two options, right? So as you can see here, there's only one way we can traverse the tree by consuming all the edges once and only once, right? How? We have to go down first and then go back and then go right, right? So we have to consume this path first and then consume this path and then consume this one last, right? So from JFK, let's say we go from this, we follow this path first, right? We go here and then we were at we're at LAX. Okay, so we don't LAX doesn't have any any path. Basically, this one will be empty. And then we just find okay LAX doesn't have any edges anymore. So we'll add this LAX to this like answer, right? And then we just we'll come back here and then it will keep going. It'll go back go up one level, so it will keep traversing down here, right? Then we'll it will come here. We'll see. Oh, it's in the Munich, right? It's the MUC airport. Does this one also have like uh, edges? Yes, they still have this one. So we'll also follow this one, go back here, right? So this one is gone. This one is gone, and then we follow back to the JFK. And then we see, oh, JFK doesn't have anything. Remember, this one is also gone, was also gone. We removed this one after we traversed to this LAX. So now JFK doesn't have any outgoing edges. So now we add this JFK to the list, right? So it's going to be LAX. We add this one, and then JFK, right? And then in the end, to the end, so the last one will be MUC, right? So that's the result. And sorry, yeah, I'm sorry. So going down, going right, and then uh, we come down here, right? So the first thing will be coming down here. The next one will be coming down here. Oh, sorry. So it's not done, right? So basically, there's one more here. So in the end, there's like one there's another LAX here in the end because uh so from JFK to MUC, right? And then from MUC to JFK. So there are gonna be two JFK here. That's two visit of JFK. So the first one will be this one. After this one, the JFK is 0. And then basically that's this JFK has doesn't have any outgoing, doesn't have any outgoing node. Then it will return JFK. But then it returns to MUC, right? MUC doesn't have it. But then in the end, remember there's like also another level of traverse here. So in the end, sorry, we'll also add JFK to this one. So basically, when we reverse it, it's going to be a JFK, MUC, JFK, and LAX, right? That's how this algorithm works. So it doesn't matter, right? So assuming, let's say we don't we didn't traverse to the right side first. Let's say we chose this, I mean we chose this path first, right? So we so we so we are coming down, right? So once we coming down here, we do a MUC, right? So does MUC have a node, right? MUC, right? And then we remove this one, right? And then does MUC have a outgoing? Yes. We go back to JFK, right? Does JFK has another one? Yes, we do go right because after we traversing down, this edge was not there anymore. So it will go right, right? And then again we'll still end up to this like LAX node first. So that's why we'll be adding to LAX, and then once we go back to the went back to the last recursion level, this one is not there, right? So does JFK has an outgoing edge? No, right? So all both of the outgoing edges have already been removed. So the JFK will be the second, and then come back to here. MUC, is there MUC? Is there like a node there? No, right? This one is gone. So third one is MUC, and the last one is still the starting point, also JFK here. So we'll be getting the same result. Uh, all right, guys, cool. So I think that's it for this problem. Yeah, hope you guys like it. Thanks so much for watching this video. Uh, okay, let me know if you guys have any comments or anything else, right? I'm thinking about like buying a video cameras. Yeah, we'll see. Okay, thank you guys. All right, see you guys soon.